Hello students, in this class I am going to explain first the force experienced by the dielectric slab between the plates of a capacitor. Now here you can see the diagram in which we have a dielectric slab of that material constant K. Now little part of that dielectric slab is inside the plates. That length of the dielectric slab inside the plates is X. You can see the diagram here. Now that is X, and you can also see the dimensions of these plates of the capacitor L and B, and these two plates are connected to a battery with constant potential V. The plates gap is D. Now this battery can provide some charge to these plates. The charge on plates of this capacitor can induce some other charge that inside this dielectric material because of induction. This induced charge on dielectric slab gets attracted by these plates of the capacitor. You can see that attracting force of this positive plate is in this direction. Attracting force of this negative plate is in this direction. The combination net force direction is this. This acts along the direction of axis of the capacitor. This force always try to bring the slab towards the center of the capacitor or into the plates of the capacitor. You can see the diagram, the force, direction of the force into the plates of the capacitor. Definitely this dielectric slab will start moving into the plates. It starts moving into the plates because of this force. To know that force of attraction, I have drawn its equivalent circuit diagram here. You can see this. So here I have divided this capacitor into two parts. A part of this is with air medium and this remaining is with dielectric slab. You can see here this C1 is with air and this remaining part with a dielectric slab of constant K, and these two are in parallel combination to that battery. So I have written capacitance of this and this. You can see how to write the capacitances of these two parts of this capacitor. Now based on this Ka epsilon naught by D, here K value for this air is 1. A means this area of the plates with air medium is B of L minus X. This part is L minus X. Clear? Because the total length of this plate is L, this is X, this remaining is L minus X. This part area is B into L minus X into epsilon naught by D. That is the capacitance of this part. And this part, capacitance of this. It is filled with dielectric material K, and this area is B into this X, this area B into X epsilon naught by D. Now these two are in parallel combination. We have this condition for parallel combination. Substitute these two. Here you will get this equation that shows effective capacitance of these two. But that you can see that effective capacitance. So as this dielectric material enters into this plate, that capacitance gradually increases and energy of this capacitor will change because of this force. Now relation between the force and energy of the capacitor is given by this. This is the conservative force which can change the potential energy of the system. F equal to minus du by dx. This U is the potential energy of electrostatic potential energy of the capacitor. You can write that half CV square. We have equation for C. V is the battery potential, which is always constant because battery maintains constant potential difference in the presence of the battery. So it is not variable during the motion of this dielectric slab into the plates. So it is constant. Only C depends on this X, not V. Substitute this here, you will have this V square by 2 constant right outside, dC by dx. C is effective capacitance of this, already we have written there, right. Now the differentiation of this, look at this carefully, differentiation of this, write these constant terms outside here, and differentiation of this with respect to x is 0, constant, L is constant, differentiation of this minus x is minus 1 with respect to x, and kx differentiation is k. This is the differentiation of that. Now I have written this clearly here, b epsilon naught by 2d and this k minus 1 v square. This is the force of attraction. Negative sign indicates attracting force. You can see this attracting force always try to bring this dielectric material into the plates, and because of that its velocity gradually increases. Because of that velocity it tends to move towards that left side of this plate, and it try to leave the plates. But when it try to leave the plates, again this attracting force will try to bring back the dielectric slab into the plates. This force always acts towards the center of the plates. So because of that attracting force, it will oscillate between these two positions. It will oscillate between these two positions like this. Clear? So its motion is oscillatory. So whether it is a simple harmonic motion or not, you can check this relation. If the force directly proportional to the displacement and in opposite direction, you can say that the oscillatory motion is simple harmonic motion. This is the condition. But here you can check this equation. This F is independent of that length of part of dielectric material inside the capacitor. So this F is directly proportional to x power 0, but not x. So its motion is not simple harmonic motion. This is the condition for simple harmonic motion, but doesn't execute simple harmonic motion. It just oscillates because this attracting force. Clear? Now you can see the time period of oscillations. So I'll have written the equation for the displacement of this up to here. Generally it starts from rest u0. So the time taken by this material to reach this to cover this distance, so with this constant acceleration. So I have substituted this s means this distance L minus x u0. So half a, already you have the acceleration based on this is F, which is equal to ma, right? M this side, you will get acceleration of that slab. Now after getting this acceleration, you can substitute this a here to get the time taken by the slab to cover this distance. Now time period of oscillation. So it will oscillate like this, to and fro motion. Up to here it looks like main position because this dielectric slab is attracted equally by these two plates. Net force acting on it is 0. So it doesn't experience force. You can say that is equilibrium state. So it will oscillate like this up to here, this main position T and extreme position. So another T and back to T. The total time period of oscillation is 4T. So that is the formula for the time period of oscillation. In the absence of the battery, charge on plates of the capacitor is constant during the oscillation of this dielectric slab. No change of the charge. But energy will change because of change of capacitance. So energy formula for this capacitor, U equal to Q square by 2C. So here Q constant, only C variable. So substitute this here to get force. Write constant terms outside, Q square by 2 d by dx of 1 by C. C is that. Now it gives F equal to minus Q square by 2 d by dx of those terms b epsilon naught by d 1 by C na. So it gives 1 by B epsilon naught by D of L minus X plus Kx. You can write this F equal to Q square by, write these terms outside, this D comes to numerator, Q square D to B epsilon naught D by dx of, you can write this in numerator, it becomes what, L minus X plus Kx power minus 1, inverse of that. So you can write now the differentiation of this. So you can see carefully that what is the differentiation of this term. The force equal to minus Q square D by 2B epsilon naught. So if it is some x power minus 1, differentiation gives 1 by x square. It gives 1 by L minus x plus Kx whole square. That is the differentiation of this. Then internal differentiation. What is the internal differentiation? This differentiation of L is 0 and differentiation of x is 1 and differentiation of Kx is k. Now it gives F equal to minus Q square by 2B epsilon naught L minus x plus Kx whole square, this in numerator k minus 1. This is the formula for force, attracting force on dielectric slab in the absence of a battery. Clear? Both the cases are important, so you should practice properly.